When you step outside and look up at the night sky, you are looking backward in time. Because light takes time to travel across the vast distances of space, the stars you see right now are images of what they looked like years, centuries, or even millennia ago. For 3 decades, our primary tool for exploring that history has been the Hubble Space Telescope. Hubble orbits 560 kilometers above the Earth, capturing the faint glow of galaxies that formed as early as 400 million years after the Big Bang. But we know older galaxies exist even further back. The problem is that they are hidden behind a cosmic wall that Hubble's optics are physically unable to penetrate. To detect the light emitted by the very first stars and galaxies in cosmic history, building a larger optical telescope wouldn't work. We had to invent an entirely different way of seeing. The universe is constantly expanding. Because of this, the oldest and most distant galaxies are moving away from us at incredible speeds. As these galaxies flee, the light they emit is subjected to a phenomenon called redshift. This means the physical speed of the galaxy moving away stretches its light waves, pulling them out of the visible spectrum and into the longer, elongated infrared spectrum. Traditional optical telescopes are physically incapable of detecting these stretched waves. To our eyes and to Hubble, this ancient light is essentially invisible. The physical laws of the expanding universe dictated the exact parameters of the machine we had to build next, an observatory optimized specifically to capture that invisible infrared light. To detect ultra-faint infrared light from 13.5 billion years ago, the telescope requires 2 specific features: a massive surface area to collect light, and a system to keep its instruments at temperatures near absolute zero. This table compares the design parameters of Hubble and its successor. While Hubble has an unobscured aperture of 4.5 square meters, the James Webb Space Telescope has 25. That's a light-collecting area 6 times larger than Hubble's. That mirror is coated in a microscopically thin layer of gold. Gold was chosen specifically because it is an excellent reflector of infrared light, bouncing those faint, ancient waves directly into the telescope's sensors. But a rigid 6.5-meter wide mirror is too wide to fit inside the 5-meter payload fairing of a standard launch rocket. Engineers solved this by dividing the mirror into 18 individual hexagonal segments made of beryllium. This allowed the mirror to be folded like origami for launch, and then unfolded once it reached space. The telescope's signature honeycomb shape isn't a stylistic choice. It is a forced reaction to the spatial limits of modern rocketry. The requirement for extreme cold presented a thermal problem. If the telescope were in a typical low Earth orbit, the heat radiating from our own planet would be enough to blind its infrared sensors. To avoid this, the telescope orbits the L2 Lagrange point, 1.5 million kilometers away. At this gravitational balance point, it keeps the Sun, Earth, and Moon completely behind its back at all times, sitting in a permanent shadow. To block that heat, the observatory uses a 5-layer sunshield the size of a tennis court. While the sun-facing side reaches 110 degrees Celsius, the dark side, where the instruments sit, chills down to negative 237 degrees Celsius. The telescope is effectively a thermodynamic fortress, engineered to survive these temperature extremes to protect its view of the early universe. Because the telescope had to be folded for launch, it had to unpack itself while coasting through the vacuum of deep space. This was a high-risk operation, with 25 years of research and $10 billion on the line. The deployment relied on 40 structures and 178 individual release mechanisms. Every single one of them had to work perfectly, as there was no way for astronauts to reach the telescope to perform repairs. The mechanics worked. In July 2022, the mission released its first full-color science images, confirming that the mirrors were perfectly focused. The success of this mechanical sequence proved that the decades of international collaboration between NASA, the ESA, and the CSA were successful. Using its infrared vision, the telescope can peer through thick clouds of cosmic dust that block visible light, revealing star-forming regions that were previously hidden. Its primary goals are to observe galaxies born just 200 million years after the Big Bang and to analyze the chemical composition of atmospheres on distant exoplanets. By measuring the star stuff within these early galaxies, scientists can track the chemical evolution of the universe and the origins of the elements required for life. By engineering a way to bypass the limits of human vision, The James Webb Space Telescope provides more than just images of distant space. It provides a record of our own cosmic origins.